Hi, today we're going to start talking about limits. So let's start with an informal definition of what a limit is. Alright, and sometimes in these definitions or theorems in math, you have to reread them a couple of times to make sure you understand everything. Every word that's in there has to be in there, and it's in there for a reason. So if the values of a function f of x approach the value L as x approaches c for some constant, we say that f has limit L as x approaches c, and the notation we use to write that looks like that. And the way we read that is we say the limit as x approaches c of f of x equals L. And we're going to go through a lot of examples to give you a better understanding of exactly what a limit is. So let's jump right in. Find the limit as x approaches 2 of the function 3x minus 2. So I started with an easy one. This is a linear function. Everybody can picture what the graph looks like. Y-intercept of -2, a slope of +3. And so we want to know what's the limit as x approaches 2. So what's happening? What are the y values approaching as x gets closer and closer to 2? So I'm actually going to call it up on the calculator. And let's look at the graph, and then I can trace along the graph. So if I put in 3x minus 2, and then hit the standard window. Now, if I press trace and I jump to 2, well, we know y is equal to 4. We could have figured that out by just plugging in 2 for x in our function. But this is asking what happens as we get closer and closer to 2. So let's say, for example, I'm over here on my graph. And as I'm approaching 2 from the left side of my graph, look at the x values, 1.36, 1.51, 1.66, 1.8. What are my y values approaching? 3.9. So at 1.96, I'm at 3.9. How about at 1.98? I'm at 3.94. How about 1.999? I'm at 3.997. So it looks like as I get closer and closer to x equal 2, my y values are getting closer and closer to 4. What if I was approaching it from the other side? What if I was up at the top there and moving my way down? So what if I were at, let's say, 3.1? Y is 7.3. How about if I'm at 2.8? Now y is 6.4. How about if I'm at 2.5? Now I'm at 5.5. How about 2.1? I'm at 4.3. How about 2.01? Now I'm at 4.03. How about 2.00001? That's really close to x equal 2. My y value is getting really, really close to 4. So no matter which side I'm traveling on this graph, as I get closer and closer to x equal 2, my y value is getting closer and closer to 4. And that's the idea of a limit. Now it may seem silly that, well, why are you doing all this work? Let's just jump to x equal 2. Well, we'll see in a few minutes why that won't be so easy sometimes. So for this, we can just actually evaluate 3 times 2 is 6 minus 2 is 4. And so that is the limit as x approaches 2 of that function. All right, let's look at another one. Now this is a graph that you probably are not familiar with. Find the limit as x approaches 0 of the rational function x divided by the square root of x plus 9 minus 3. Well, you're not familiar with this graph, but you might think, well, why don't I just plug in 0 for x like I did before? Plug in the number for x and then simplify. If you plug in 0 here, you're going to get 0 over the square root of 0 plus 9 minus 3, which is going to give you 0 over the square root of 9 is 3 minus 3 is 0. You get 0 over 0. And so you think, oh, it's impossible, so I can't do this limit. Well, that's actually not true. So let's take a look at the graph. And I'll have to be careful how we punch this in. So it's x divided by, and I'm going to use parentheses to get the whole denominator. So the square root of x plus 9, get outside the square root, and then a minus 3, and then close my parentheses. Now when I hit graph, now I'm trying to find the limit as x approaches 0. So if I hit trace, you can see at 0, y is not defined, which we know because we get 0 over 0 when we tried to plug it in. But it does look like as my graph is approaching x equals 0, there is some y value that it's approaching. So that's where I'm going to go ahead and say, well, what if I'm over here at -1? My y value is 5.82. How about if I was a little bit closer to x equals 0? How about -0.5? Now my y value is 5.915. How about if I was even closer to x equals 0, like -0.1? Now my y value is 5.98. So does it seem like I'm approaching a specific y value? Let me get a little closer to x equals 0. How about -0.001? Oh boy, I'm at 5.99983. So I think it's a pretty good guess that it looks like I'm getting close to 6 as x gets close to 0. What if I was over on the positive side and I was traveling, getting closer and closer to x equals 0? Well, looking at my y values, 6.07, 6.05, 6.02. How about if I just go x equals 0.1? I'm at 6.016. How about x equals 0.0001? And notice on the calculator it puts the x in scientific notation. And I'm at, the y value is 6 and then 4 zeros and then a 167. So I think we're pretty confident from tracing on the graph, even though this function is not defined at 0, the limit as x approaches 0 is equal to 6. And so that's the really, really important concept of limits. And I've spelled it out here for you. Finding the limit of a function, f, at a value x equals c does not depend on the existence of f of c. So we really don't even care what happens at that c value. We just care what's happening with our graph as we get closer and closer to x equals c. So it doesn't matter what happens to our function f at x equals c. The limit is the value that the function is approaching. And I can't stress that enough. And it requires a little bit of different thinking. But the value that the function is approaching as x gets closer and closer to c. All right, let's look at a few more examples. How about the limit as x approaches 2? Well, immediately you can see that we can't just plug in 2 for x because that would give our denominator a value of 0, and we can't divide by 0. So I know that if I graph this, there's a hole in my graph at x equals 2. But I'm wondering, maybe as I'm getting closer and closer to x equals 2, I'm approaching a certain y value. And how can I figure that out? Well, I can keep doing what I was doing. I could use the calculator and I could graph it and take a look and do some tracing. Or maybe I can use some of all that algebra work we've done in the previous years and see if I can simplify this expression. So let me look at the top, and I think maybe I could factor. And since there's 4 terms, I remember that factor by grouping was one of the techniques. So let me look at the first 2 terms, and I can factor out an x squared. And I'm left with an x minus 2. Go ahead and distribute that, and you'll see that it's what we started with. And then if I look at the 3rd and 4th terms, I could factor a 2 out of those. And when I factor out a 2, I'm left with an x minus 2. And all of that is over x minus 2. So I'm trying to do the limit as x approaches 2 of this. Now in the numerator, I really have 2 terms. There's one, there's the other. They both have a common factor of x minus 2. So I can factor x minus 2 out of both of those terms, and I'm left with an x squared from the first green box, and then plus a 2 from the second green box over x minus 2. And lo and behold, we can cancel factors, so those cancel out. And so now x squared plus 2, and here's where some understanding of this. This graph, y equal x squared plus 2, and we know what that looks like. That's a parabola shifted up 2 units. That graph is exactly the same as this graph, except this graph happens to have a hole at x equals 2. And so if I graph that original rational function, it would look exactly like this parabola I drew down here, except it would have a hole here. Oops, not there. It would have a hole in it at x equals 2, which would be somewhere over here. So I can actually look at the simplified version, which is almost the exact same graph, and now I could plug 2 in for x there. 2 squared is 4 plus 2 is 6. So I'm guessing the limit is equal to 6. Let's verify that. I'm going to go ahead and graph this complicated looking function. So I'm going to use parentheses for the top, and I have x to the third power minus 2x squared plus 2x minus 4 divided by another set of parentheses, x minus 2. And sure enough, it looks like that parabola, except if I hit trace and I type in 2, it's undefined. But we know as I'm getting close to 2, like 1.9999, y is getting close to 6. Because on my simplified version of the expression, I could actually plug in 2 and it evaluated to 6. So that verifies for me that I found the limit. How about a piecewise function? Let f of x equal 1 when x is not 5, and let it equal negative 2 when x equals 5. Well, let's take a look at this graph. This should be a pretty easy one to graph. F of x is equal to negative 2 almost all of the time. So the only time it's not is when x is equal to 5. So that just tells me, oh, I'm sorry, I have that backwards. The function is equal to 1 almost all the time, as long as x is not equal to 5. Let's get color coordinated here. All right, let's try it again. So except for at x equals 5, my function is equal to 1. That's supposed to be a nice horizontal line. Oh well, I did my best. All right, so the function equals 1 when x is not 5. And when it is 5, the function equals negative 2. So there's actually a single point right down here. So this is my function f. Now, what's the limit as x approaches 5 for this function? Well, once again, it isn't as simple as saying, oh, just evaluate f of 5. Because if I did that, I'd say the answer is negative 2. But that actually is not the answer for the limit for this. So what we have to always remember is that what happens as we're traveling along this graph. So if I have a point, and I'm getting closer and closer and closer to x equals 5, what are my y values? Well, it's constant, so it's 1, 1, 1, 1, 1, 1, 1. If I'm over on this side coming in, 1, 1, 1, 1, 1, 1. So even though when we finally get there it jumps down to here, we don't care what happens when we actually get to x equal 5. The limit is concerned about what happens as x approaches 5. And so for that, our limit is equal to positive 1. All right, let's look at just a few more examples. How about the limit as x approaches 0 for this function? Well, we could go ahead and graph this. And that's what our graph is going to look like. For example, if x is 8, if I'm making a t-table here, well, I won't even, I'll just write it on the side. If x is, let's say, 8, I'm going to get 8 over the absolute value of 8, which is 8, and I get 1. When x is 5, I'm going to get 5 over the absolute value of 5, which is 5, so I get 1. So we're good. How about when x equals 0? Well, I get 0 over the absolute value is 0. That's undefined, so that's why there's no value for this function at 0. How about negative values? How about x equals negative 1? Well, then I get negative 1 over the absolute value of negative 1, which is positive 1, and that gives me negative 1. How about when x equals negative 3? Well, I get negative 3 over the absolute value of negative 3, which is a positive 3, and that gives me negative 1. So that should make sense then why the graph should look like that. Now, I want to know what's the limit as x approaches 0. And we have a little bit of a problem here. Because what if I'm approaching it from this side? As I'm approaching x equals 0, my y values are negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. So it would be negative 1. But what happens if I happen to be on this side and I was approaching x equals 0 from the right? Then I have positive 1, positive 1, positive, positive 1. So the limit would be positive 1. So in this case, it's really important to consider which side we're approaching the x value from. And so these are called one-sided limits when you analyze it this way. On those other graphs, it wasn't a problem because from either side we were approaching the same value. But that's not the case here. So the way we read this is the limit as x approaches 0 from the left. That's what this negative sign means here, and it's after the number. It's not in front of the number. So that means we're coming from the left side. From the left. So as we're traveling on our graph, from this side, getting closer and closer to x equals 0, what's our limit? Well, it's just constant, negative 1, negative 1, negative 1, negative 1. So this limit is going to be negative 1. On the other hand, what if we were approaching x equals 0 from the right, and that's what that means, the plus after it. And so that would be this situation where we're moving along here, and we have 1, 1, 1, 1, 1. So that, from that direction, the limit is positive 1. And so therefore, when I ask what's the limit as x approaches 0, our answer is going to be does not exist. Because coming in from the left side, we get one answer, and coming in from the right side, we get another answer. And we'll usually abbreviate this, does not exist. And that leads to an important rule with limits. If the left and right-hand limits are not the same, then the overall limit does not exist. All right, a couple more examples. What's the limit as x approaches 0 of 1 over x squared? Well, that's the graph of 1 over x squared. So now as I'm approaching 0 from the left side, you can see that it's going up and up and up and up, and it keeps going up to infinity. And if I'm approaching from the right side, it's also going up to infinity. So in this case, we would say the limit does not exist, but we could actually be more specific and say that it's approaching positive infinity. And so I would like you to be more specific on these types of answers, even though some textbooks are not. And I would like you to say it's approaching infinity. And I'll show you why with my next example. How about the limit as x approaches 0 of just 1 over x? Now, if we're approaching from the left side, as x gets closer and closer to 0, our point is getting further and further down, so it's going to negative infinity. But if I'm approaching x equals 0 from the right side, my y values are going up and up and up and up to positive infinity. So for this one, I would say the limit does not exist, and that's it. I can't say negative infinity, I can't say positive infinity. However, if I said, what's the limit as x approaches 0 from the left of 1 over x, then you would say, well, it doesn't exist, but you can be more specific and say negative infinity. Or if I ask, what about the one-sided limit as x approaches 0 from the right? And then you would say it doesn't exist, but more specifically, it goes to positive infinity. All right, and so that's what I wrote down on that one. How about this one? What's the limit as x approaches 0 of sine of 1 over x? Well, you probably are not familiar with what that graph looks like. So let's go ahead and graph that. Now, clear. Let's do sine of 1 over x, and if it's not specified, let's make sure we're always in radian mode. So sine of 1 over x, graph. Oh, let me hit zoom 7 for zoom trig. Okay, so as x approaches 0, it's hard to tell. There's a lot of stuff going on in there. So maybe I should zoom in. So let me hit zoom 2, enter. Oh man, it's really jumping up and down. Now we know it's not defined at 0. If I trace, when x is 0, y doesn't have a value because the fraction is 1 divided by 0. But as I get close, it's jumping all over the place. Maybe I should zoom in one more time. Let's zoom in. Oops. Let's zoom in. And I want to zoom in right around here at 0, 0. There we go. Enter. Oh my gosh, it even gets worse. And so it turns out the more we zoom in, the more this function oscillates and jumps up and down and up and down and up and down. So it keeps jumping up, positive, negative, positive, negative. And so it's actually not approaching any specific value. So this is one of those weird ones, and the limit does not exist because this function keeps oscillating as we get closer and closer to 0, so that it does not have a limit. All right, let's try another one. Now that you kind of know the tricks of all the types of things that are going to happen, find this limit. And it's probably a good idea if you want to hit pause, come up with your answer, and then check it. This one I like doing because now students tend to look at the top and say, oh, I could factor that. X plus 5, x minus 5, and then I could cancel the x plus 5s. And then, oh, now I can just plug in 5, and I get 5 minus 5 is 0 over 3. So 0, is that the answer? And my question is, why did you even bother doing this factoring and canceling? The first thing you should always do when you're evaluating limits, I'll say that again, the first thing you should always do when evaluating limits is see if you can plug in that value directly, especially for a function that is smooth and doesn't have any breaks in it. This has a break at negative 5. Negative 5 would make that a divide by 0. But at positive 5, it's fine. So I can go ahead and plug in 5 on the top, and I'm going to get 0. And when I plug 5 in on the bottom, I'm going to get 30. And so, sure enough, and you could check on a graph, that limit is just 0. All right, how about this one? Once again, you might want to hit pause, put your answer, and then see if you're right. What's the limit as x approaches c of x squared plus 1? Well, x squared plus 1 is a nice smooth parabola. There's no holes or breaks in the graph. So I'm just going to plug in c for x, and it's c squared plus 1 for whatever c is equal to. All right, let's look at one last one. What's the limit as x approaches negative 1 of the square root of x minus 1? Well, if we plug in negative 1 for x, we're looking at the square root of negative 2, and we can't do that in the real number system, so this is a does not exist. And if you think about the graph for the square root of x minus 1, you know what the square root of x graph looks like. And so a minus 1 on the inside will shift it 1 to the right. And so if we're trying to figure out what happens as we get closer and closer to x equals negative 1, well, the closest we can get is here. It never gets even close to negative 1 over here because our graph stops right here. So it does not exist.